Right, in this video we're going to turn to max and min problems for multivariable functions. So let's say we have a function f that depends on x and y and it's defined on some domain D. Okay, we say that at a point AB we have a local maximum if f of AB is greater than or equal to f of xy for x, y, and d around AB. And we have an absolute maximum if f of AB is greater than or equal to f of xy for all xy across the entire domain D. Okay, so put another way, if we're at an absolute maximum, we are at a point on our surface where the z coordinate, right, the output value f of AB is as large as possible. And that's going to happen here at this peak. Okay, now for a local maximum, say at this point right here, note that the z coordinate is not as large as possible. That happens over here, right? However, if we stay local to this point, right, we only consider xy around AB, then this is the point where the z coordinate is as large as possible. And likewise at that peak as well as this peak, right, where we have this absolute max. Now for local min and absolute mins, same idea, except now, right, we are minimizing the output values. So if f of AB is less than or equal to f of xy for xy around AB, then we have a local min. For absolute mins, if f of AB is less than or equal to f of xy for all xy across the entire domain D. Okay, so here we have our absolute min where the z coordinate is as small as possible. And then at this point, right, as long as we stay local, then that is the location where the z coordinate is as small as possible. All right, cool. So now how do we find the local extrema of a function of a single variable? Well, we started out by finding the critical points. So what are critical points for a multivariable function? Well, we say that a point AB in the domain of f is a critical point if either these two partial derivatives, so the x derivative of f at AB and the y derivative of f at AB, are both 0, or if one or both of these partial derivatives is undefined. Okay, so now remember, for a single variable function f, a critical point was a number c where either f prime of c was 0, okay, that's the analog of this condition, or if f prime of c was undefined, that's the analog of this second condition. Okay, now one thing to note here, let's say we're at a peak on our surface, right? We have a local max right here. Well, since we're at this flat spot, the slope of our surface in the positive x and in the positive y directions is 0. Okay, so that would be an illustration of this first condition here. Okay, another thing to point out is that since the gradient of f at AB is this vector whose I component is the x derivative of f at AB and whose j component is the y derivative of f at AB, to say that AB is a critical point of f is equivalent to saying that either the gradient of f at AB is the 0 vector, that would be this first condition right here, or if the gradient is not defined. That would happen if one or both of these partial derivatives is undefined. Okay, now let's turn to the following key theorem. It says that if f has a local max or min at AB, then AB is a critical point of f, which is a direct analog of the main theorem we saw in the last video on local extrema and critical points. So this leads us to the following result, okay? If I want to classify critical points of a multivariable function, okay, I want to do what? Well, I'm going to first find those critical points, and then I'm going to test the critical points. Okay, so how do I test? Well, in the last video for single variable functions, we have either the first derivative test or the second derivative test available to us. We don't really have an analog to the first derivative test for a multivariable function because we're looking at a surface as opposed to just a curve. Okay. However, we do have a second derivative test available to us. So let's go ahead and state that here. It says if AB is a critical point of f, let this quantity capital D of AB be defined as follows. Okay, so we multiply the xx and the yy derivatives of f evaluated at AB, and then we subtract from that product the square of the mixed partial derivative of f at AB. Okay, now it turns out that if this quantity D is positive, and the xx derivative of f at AB is also positive, or the yy derivative of f at AB is positive, so either or, then f has a local minimum at AB. Okay, remember the xx derivative of f measures the concavity of our surface in the x direction. So here at AB, we're saying we have positive concavity in the x direction. This would say we have positive concavity in the y direction. Okay, that's implying that we have a local minimum. All right, now if this quantity d is positive and the xx derivative or the yy derivative were negative at AB, then we would have a local maximum. Okay, this feels pretty similar to the result we saw in the last video for the second derivative test. Now here, if this quantity d is negative, then we say that f has a saddle point at the point AB, and we'll see some examples in the next couple videos of what a saddle point can look like. But here, as you can see, I've drawn a portion of a surface where we have a saddle point right here. It looks kind of like a, well, horse saddle, right? So at this point, it's not a max or a min, right? If I'm standing right here, if I move right along this purple cross section, my z coordinate is going to decrease. But if I move along this yellow cross section, then my z coordinate increases. So a saddle point is neither a local max or min. Now, lastly, it can happen where d at AB is equal to 0. And in this scenario, the test is inconclusive. This is kind of what we saw in the last video for the single variable second derivative test, right? If f double prime at c were 0, the test is inconclusive. So here we're just going to have to try something else, and we'll see some examples in the next few videos to illustrate what that will look like. All right, so with this all in place, we will start doing some examples in the next video. All right, see you there.